According to the National Electrical Code, Section 210.20a, circuit conductors must possess an ampacity that is not less than the circuit's maximum load current. In a situation where the load current is 14.5 amps, a number 12 wire used from the breaker to the watt-stopper relays line side is generally sufficient, assuming it meets other requirements like overcurrent protection. The National Electrical Code Section 210.19 dictates that conductors connected to terminals or splicing devices should be terminated in a way that is suitable for the conductor material. This means the terminals of the breaker and the lighting control unit need to be capable of accommodating the number 12 and number 8 conductors respectively. Essentially, the terminals must be properly rated for the size of the conductors being used. If the terminals of the breaker and the lighting control unit can accommodate the number 12 and number 8 conductors, and the length of the number 12 wire is less than 48 inches, the proposed installation would generally be compliant with the National Electrical Code, assuming all other applicable codes and standards are met. The electrician's concern about using different wire sizes in a circuit often stems from several important considerations. Firstly, ampacity matching is crucial. The National Electrical Code mandates that circuit conductors must have an ampacity equal to or greater than the maximum load current. If the smaller number 12 wire is adequately rated for the 14.5 amps load, this part of the code is satisfied. Secondly, termination suitability is essential. National Electrical Code Section 110.14 requires that terminations and splices be suitable for the conductors used and properly installed and torqued. This means that the devices to which the number 12 and number 8 wires are connected must be designed to accept those specific wire sizes and types, and that the connections must be made according to the manufacturer's instructions, often involving specific torque values. Thirdly, overcurrent protection coordination is a major safety factor. The circuit breaker protects the conductors from overloads and short circuits. The breaker's amp rating must be appropriate for the smallest conductor in the circuit. In this case, the number 12 wire. If the number 12 wire is rated for 20 amps, a 20 amp breaker is generally suitable, assuming that the connected load does not exceed 80% of the breaker rating for continuous loads, as per National Electrical Code 210.20a. Fourthly, voltage drop is also a significant consideration. While the larger number 8 conductors are used to mitigate voltage drop over a longer distance, the short run of number 12 wire, less than 48 inches, is unlikely to introduce a problematic voltage drop. However, it is always advisable to calculate the voltage drop to ensure it remains within acceptable limits, typically 3% for branch circuits, as recommended in National Electrical Code 210.19 Informational Note Number 1. Fifthly, the listing and labeling requirements are there to provide guidance. All electrical equipment must be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories Incorporated or Electrical Testing Laboratories. This listing ensures that the equipment has been tested and found safe for its intended use. The equipment's labeling will specify the types and sizes of conductors that can be connected to it, which is a crucial factor in ensuring a safe and code-compliant installation. Sixthly, local amendments and interpretations are important to remember. Local jurisdictions may have amendments to the National Electrical Code or interpretations of the code that are stricter than the National Electrical Code itself. It is always necessary to check with the local electrical inspector to ensure compliance with all applicable regulations. In summary, while the National Electrical Code does not explicitly prohibit using a smaller gauge wire for a short run in this type of scenario, several conditions must be met to ensure a safe and code-compliant installation. The number 12 wire must be adequately rated for the load, the terminations must be suitable for the conductors used, the overcurrent protection must be appropriate, and the voltage drop must be within acceptable limits. The devices need to be listed for the application. Local codes should be verified. If all of these conditions are met, the installation is likely to be compliant with the National Electrical Code. Several factors can affect the ampacity of conductors, requiring careful consideration during electrical installations. The ambient temperature around a conductor influences its ability to dissipate heat. Higher temperatures reduce ampacity, necessitating the use of correction factors found in National Electrical Code Table 310.15 Bone. The number of current-carrying conductors bundled together in a raceway or cable also affects ampacity. Bundling reduces heat dissipation, requiring the application of adjustment factors as specified in National Electrical Code Table 310.15b. The insulation type of a conductor determines its maximum operating temperature, which directly affects ampacity. Common insulation types include THHN, THHW, and XHHW, each with different temperature ratings and ampacities as listed in National Electrical Code Table 310.16. The presence of harmonics in an electrical system can increase the current flowing through the neutral conductor, requiring it to be upsized to prevent overheating. National Electrical Code 220.61 Cohen addresses neutral conductor sizing in such scenarios. Continuous loads, defined as loads that operate for 3 hours or more, require conductors to be rated for 125% of the continuous load current as per National Electrical Code 210.20a. This ensures that conductors do not overheat during prolonged operation. The type of raceway or cable in which conductors are installed affects their ability to dissipate heat. Open wiring allows for better heat dissipation compared to conductors installed in conduits, influencing ampacity. The directing factors provided in National Electrical Code Table 310.15b3 are used to adjust the ampacity of conductors based on the number of current-carrying conductors in a raceway or cable. These factors account for the reduced heat dissipation due to bundling. Voltage drop is an important consideration in electrical installations to ensure that equipment receives adequate voltage. The National Electrical Code provides guidelines and recommendations for minimizing voltage drop. National Electrical Code 210.19 Informational Note Number 1 recommends limiting voltage drop to 3% for branch circuits and 5% overall for feeders and branch circuits combined. Excessive voltage drop can cause equipment to malfunction, overheat, or operate inefficiently. It can also lead to nuisance tripping of circuit breakers. The formula for calculating voltage drop in a single-phase circuit is voltage drop equals 2 times K times I times D divided by circular mils, where K is the conductor material constant, I is the current in amps, D is the one-way distance in feet, and circular mils is the conductor's cross-sectional area. Increasing the conductor size reduces voltage drop because a larger conductor has a lower resistance, as it is inversely proportional to the cross-sectional area of the conductor. Reducing the length of the circuit also reduces voltage drop because voltage drop is directly proportional to the length of the conductor run. Using conductors with lower resistance materials, such as copper instead of aluminum, reduces voltage drop because copper has a lower resistivity than aluminum. Keeping connections tight and clean minimizes voltage drop at connection points. Loose or corroded connections increase resistance and contribute to voltage drop. Balancing the load across all phases in a 3-phase system helps to minimize voltage drop. An unbalanced load can cause excessive current flow in one or more phases, leading to increased voltage drop. Using a higher voltage level, such as 480 volts instead of 208 volts, reduces voltage drop because the current is lower for the same amount of power. Regular maintenance and inspection of electrical systems helps to identify and correct voltage drop issues before they become major problems. Using voltage drop calculators or software tools simplifies the process of calculating voltage drop for different circuit configurations and conductor types. National Electrical Code Chapter 9 Table 8 provides the circular mils for different conductor sizes, which is necessary for calculating voltage drop. The conductor material constant, K, is typically 12.9 ohms circular mils per foot for copper and 21.2 ohms circular mils per foot for aluminum. Overcurrent protection is a critical aspect of electrical safety, designed to protect conductors and equipment from damage caused by excessive current flow. The National Electrical Code provides detailed requirements for overcurrent protection devices. Circuit breakers and fuses are the two main types of overcurrent protection devices. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overcurrent condition is detected, and they can be reset. Fuses are single-use devices that melt and open the circuit when an overcurrent condition occurs, and they must be replaced after activation. The amp rating of an overcurrent protection device must be selected to protect the conductors it serves based on the conductor's ampacity. National Electrical Code 240.4b allows for the next highest standard overcurrent device rating to be used if the conductor ampacity does not match a standard overcurrent device rating under certain conditions. Overcurrent protection devices must be located at the point where the conductors receive their supply, such as at the panel board or transformer. National Electrical Code 240.21 provides specific rules for overcurrent protection of tap conductors. Overcurrent devices must be readily accessible so that they can be easily inspected, tested, and replaced. National Electrical Code 240.24 specifies the requirements for accessibility of overcurrent devices. Overcurrent protection devices must be suitable for the available fault current at their location. High fault current can cause overcurrent devices to fail catastrophically if they are not properly rated. The interrupting rating of an overcurrent device is the maximum fault current that the device can safely interrupt without failing. Overcurrent devices must have an interrupting rating that is equal to or greater than the available fault current. Time current curves illustrate the relationship between the magnitude of overcurrent and the time it takes for an overcurrent device to trip or open. These curves are used to coordinate overcurrent devices in a system to ensure that the closest device to the fault opens first. Selective coordination of overcurrent devices ensures that only the overcurrent device closest to the fault opens, minimizing disruption to the rest of the electrical system. National Electrical Code 240.12 provides requirements for selective coordination in certain applications. Ground fault protection is a type of overcurrent protection that detects and interrupts ground faults, which are unintentional connections between a current-carrying conductor and ground. Ground fault circuit interrupters are required in many locations, such as bathrooms, kitchens, and outdoor areas to protect people from electric shock. Arc fault circuit interrupters are designed to detect and interrupt arc faults, which are dangerous electrical arcs that can cause fires. Arc fault circuit interrupters are required in many locations, such as bedrooms and living rooms, to protect against electrical fires. Regular testing and maintenance of overcurrent protection devices is essential to ensure that they function properly when needed. Circuit breakers should be periodically tested to verify their tripping characteristics. Fuses should be inspected to ensure that they are not damaged or deteriorated. National Electrical Code Article 230 covers service entrance conductors and equipment, including overcurrent protection requirements. Article 240 covers overcurrent protection in general, including requirements for overcurrent devices, conductor protection, and coordination. Short-circuit current ratings are a critical consideration in electrical system designed to ensure that equipment can safely withstand the high currents that flow during a short-circuit fault. A short circuit occurs when there is an unintended low-resistance path between two or more conductors, resulting in a large surge of current. The available short-circuit current is the maximum current that can flow at a particular point in the electrical system during a short circuit. The short-circuit current rating of electrical equipment is the maximum short-circuit current that the equipment can safely withstand without sustaining damage. Electrical equipment must have a short-circuit current rating that is equal to or greater than the available short-circuit current at its location. The short-circuit current rating of equipment is typically marked on the equipment's nameplate. Conducting a short-circuit study is essential to determine the available short-circuit current at various points in the electrical system. A short-circuit study involves calculating the impedance of the electrical system components, such as transformers, conductors, and protective devices, to determine the fault current. The infinite bus method is a simplified method for calculating short-circuit current, assuming an infinite source of power. Point-to-point calculations are a more detailed method for calculating short-circuit current, taking into account the impedance of each component in the electrical system. Software programs are available to automate the process of performing short-circuit studies. The symmetrical components method is a mathematical technique used to analyze unbalanced faults in three-phase systems. Protective devices, such as fuses and circuit breakers, play a crucial role in limiting the duration and magnitude of short-circuit currents. Current-limiting fuses are designed to quickly interrupt short-circuit currents, minimizing the stress on downstream equipment. Circuit breakers with high interrupting ratings are used to protect equipment from high fault currents. The coordination of protective devices is essential to ensure that the device closest to the fault opens first, minimizing the impact on the rest of the electrical system. Grounding and bonding are critical for electrical safety, providing a low impedance path for fault currents to return to the source, thereby facilitating the operation of overcurrent protective devices. Grounding refers to the connection of the electrical system to the earth, providing a reference point for voltage and stabilizing the system. Bonding refers to the connection of non-current carrying metal parts to create a continuous electrical path, ensuring that all metal parts are at the same potential. The grounding electrode system consists of electrodes, such as ground rods, ground plates, and metal water pipes, that are used to connect the electrical system to the earth. The grounding electrode conductor connects the neutral point of the electrical system to the grounding electrode system. The equipment grounding conductor provides a path for fault currents to return to the source from non-current carrying metal parts. The main bonding jumper connects the equipment grounding conductor to the neutral conductor at the service entrance. Supplementary grounding electrodes are used to improve the effectiveness of the grounding system in areas with high soil resistivity. National Electrical Code Article 250 provides detailed requirements for grounding and bonding. Ground fault circuit interrupters protect people from electric shock by detecting and interrupting ground faults. Ground fault protection of equipment protects equipment from damage caused by ground fault. Isolated ground receptacles are used to reduce electrical noise in sensitive electronic equipment. Bonding jumpers are used to bond metal raceways, enclosures, and other metal parts to create a continuous electrical path. Regular inspection and testing of grounding and bonding systems is essential to ensure their effectiveness. National Electrical Code 250.50 covers the grounding electrode system, including requirements for different types of electrodes. National Electrical Code 250.118 lists the types of equipment grounding conductors that are permitted by the code. The impedance of the grounding path affects the magnitude of fault current and the speed at which overcurrent devices operate. A low impedance grounding path is essential for effective overcurrent protection. The size of the grounding electrode conductor is determined based on the size of the service entrance conductors, as specified in National Electrical Code Table 250.66. The size of the equipment grounding conductor is determined based on the rating of the overcurrent device protecting the circuit, as specified in National Electrical Code Table 250.122. The continuity of the grounding path is essential for electrical safety. Any breaks or discontinuities in the grounding path can compromise the effectiveness of the grounding system. National Electrical Code 250.2 requires that the grounding and bonding system be designed and installed in a manner that is permanent and effective. Electrical enclosures and junction boxes serve to protect electrical connections and equipment from environmental factors and physical damage. Enclosures and junction boxes must be suitable for the environment in which they are installed, such as wet, damp, or corrosive locations. National Electrical Code Article 314 covers the requirements for outlet boxes, device boxes, and junction boxes. Metallic enclosures and junction boxes must be grounded to provide a path for fault currents to return to the source. Non-metallic enclosures and junction boxes are typically used with non-metallic wiring method. The size of enclosures and junction boxes must be adequate to accommodate the conductors, splices, and devices installed within them. National Electrical Code 314.16 provides rules for calculating the number of conductors permitted in a box. Enclosures and junction boxes must be securely mounted to provide support and prevent movement. Enclosures and junction boxes must be accessible for inspection, testing, and maintenance. Enclosures and junction boxes must be listed and labeled by a recognized testing laboratory. The type of enclosure or junction box required depends on the specific application and environmental conditions. Weatherproof enclosures are used in outdoor locations to protect against rain, snow, and ice. Dust-tight enclosures are used in dusty environments to prevent dust from entering the enclosure. Explosion-proof enclosures are used in hazardous locations where flammable gases or vapors may be present. Corrosion-resistant enclosures are used in corrosive environments to protect against corrosion. National Electrical Code 314.17 covers the requirements for the securement of boxes. National Electrical Code 314.27 covers the requirements for boxes in concrete or tile. The volume of the enclosure or junction box affects the number of conductors that can be installed within it. The volume of the enclosure or junction box is typically marked on the box. Conductors must be properly supported and secured within enclosures and junction boxes. Cable clamps, connectors, and other fittings are used to support and secure conductors. National Electrical Code 300.4 requires that conductors entering enclosures or raceways be protected from abrasion. Wiring methods refer to the various types of cables, conduits, and raceways used to route electrical conductors. The National Electrical Code specifies the requirements for different wiring methods. Non-metallic sheathed cable is a common type of wiring method used in residential and light commercial buildings. It consists of two or more insulated conductors enclosed in a non-metallic jacket. Armored cable consists of insulated conductors enclosed in a flexible metal armor. Electrical metallic tubing is a thin-walled metal conduit used to protect conductors. Rigid metal conduit is a thick-walled metal conduit used to protect conductors in harsh environments. Liquid-tight flexible metal conduit is a flexible metal conduit with a liquid-tight jacket used in wet locations. Underground feeder and branch circuit cable is used for underground wiring installations. Cable trays are used to support and route large quantities of cables in industrial and commercial buildings. Wireways are metal troughs used to protect and route conductors. Raceways are enclosed channels designed to hold wires or cables. National Electrical Code Chapter 3 covers the requirements for wiring methods and materials. The type of wiring method used depends on the specific application, environmental conditions, and code requirements. Conductors must be protected from physical damage, moisture, and other environmental factors. Conductors must be supported and secured to prevent strain on connections. Conductors must be properly sized for the load they will carry. Conductors must be identified as to their purpose. National Electrical Code 310.15 provides ampacity tables for different types of conductors. National Electrical Code 310.4 requires that conductors be installed in a neat and workmanlike manner. The bending radius of conductors must be sufficient to prevent damage to the insulation. The dirting factors for conductors installed in raceways or cables must be applied as necessary.